Welcome to This Explainer. Today, we're taking a journey to the absolute boundaries of our universe. But, we aren't traveling to the edge of space, we're traveling to the edge of scale. We're going to discover exactly what happens when you zoom in so far and things get so incredibly extreme that the very laws of physics as we know them just completely break down. To set the stage for how wild things get at these boundaries, I want you to imagine a temperature of 1.41 times 10 to the 32 Kelvin. This is what we call the Planck temperature. It's so terrifyingly high that if you were to heat a piece of metal to this point, it would instantaneously vaporize into a burst of pure energy before the heat could even begin to spread through it. For some context here, the hottest temperature ever created in a human lab is about 5.5 trillion degrees Celsius, and the core of our sun, that's a measly 15 million degrees. But this number, we're talking about 100 million trillion degrees. At this extreme, the fundamental forces of nature might actually unify into a single force, and our current understanding of physics simply shatters. And that brings us to a fundamental mystery that physicists have been wrestling with for well over a century. What is the smallest possible distance in the universe? Like, is there a hard physical limit to how far down we can zoom into the fabric of reality? We know matter is made of molecules, right? Which are made of atoms, which are made of protons and electrons, and those are made of quarks. But does it just keep going forever, or is there essentially a fundamental pixel of space? Now, the quest for these natural limits didn't actually start with modern particle colliders. It started over a century ago with pioneers who wanted to understand the universe totally free from human biases. Back in 1874, George Stoney noticed that electric charges quantized and derived natural units of length and time. Then, in 1899, the brilliant Max Planck proposed his own universal units, and this was a full year before he even formally introduced quantum theory. Later on, in 1955, John Wheeler began theorizing about what actually happens to spacetime at these incredibly tiny scales. The sheer ambition behind Max Planck's thinking was just staggering. As he wrote in 1899, he recognized that our standard units, like meters and seconds, are completely arbitrary. They're based solely on our terrestrial needs here on Earth. He wanted units that would retain their significance across all times and all cultures, even extraterrestrial ones. By combining fundamental constants of nature, he aimed to create a truly universal measurement system that you could apply absolutely anywhere in the cosmos. So, how exactly did he pull this off? Well, Planck took three universal constants: c, the speed of light; g, the Newtonian gravitational constant; and his own h-bar, the reduced Planck constant representing quantum action. By mathematically combining these, we get the exact numerical extremes of our reality: the Planck length, time, mass, and temperature. In this system of units, those fundamental constants effectively equal 1. It's literally physics stripped of all human perspective. To really put into perspective just how tiny these units are, the Planck length is 1.6 times 10 to the negative 35 meters. That is so unimaginably small that a single standard meter stick contains roughly 61 decillion of them. Yeah, that's a 61 followed by 33 zeros. Now, the Planck mass is actually quite ordinary. It's about 22 micrograms, which is roughly the mass of a flea egg. But the Planck length and Planck time, those represent scales that are just mind-bogglingly minuscule. All right, let's move into part 1, the vast unknown, also known as the desert of scales. So, between the subatomic particles we can observe today and the Planck scale we just defined, there is this vast, unobservable gap. And why does this hidden desert matter? It matters because right at the Planck scale, our two most successful but entirely incompatible frameworks of reality violently collide. On one hand, we've got Einstein's general relativity, which tells us spacetime is smooth and continuous, perfectly governing stars and gravity. On the other hand, we have quantum mechanics, which tells us reality is probabilistic, jittery, and governed by the Heisenberg uncertainty principle. Macroscopically and subatomically, they work perfectly in their own separate domains. But at the Planck scale, they both try to take over, and the math just completely breaks down. When these two theories clash, the result is a wild concept called quantum foam. Proposed by John Wheeler in the 1950s, this is the theoretical state where that smooth, continuous spacetime of relativity breaks down completely. At distances of 10 to the negative 35 meters, quantum fluctuations become so extreme that spacetime itself becomes a chaotic, bubbling, turbulent foam. So our everyday familiar notions of distance and time, they literally cease to apply. Now, you might think this is all just abstract math, but we actually see current physics fail precisely at these Planck scale extremes out in our own universe. For instance, we cannot describe the very first fraction of a second of the Big Bang, the so-called Planck epoch before 10 to the negative 43 seconds. We also can't describe the center of black holes, where matter collapses into points of infinite density known as singularities. So, to really understand the beginning of the universe and the ultimate fate of matter, we desperately need to understand the Planck scale. So, you're probably wondering, if this scale holds the ultimate secrets to the universe, what's the holdup? What's the experimental roadblock here? Why can't scientists just build a super powerful particle accelerator, like a massively scaled up version of CERN's Large Hadron Collider? Smash some particles together and observe the scale directly.
Well, the experimental roadblock is honestly staggering. According to astrophysicist Avi Loeb, relying on limits derived by Julian Schwinger back in 1951, reaching the Planck energy is effectively impossible. To get a single proton to that energy, you'd need an electric field spanning an accelerator 10 times larger than our sun. And if you tried to cheat and just make the field stronger to build a smaller machine, the vacuum itself would break down, spontaneously creating electron-positron pairs right out of nowhere.
But hey, let's pretend for a second we could actually build that impossible solar system-sized machine. Even then, the cross-section for a Planck energy interaction is so incredibly tiny that only 1 in 10 to the 41st power collisions would actually hit the target. The rest would just result in a useless shower of lower energy particles. You would literally need an energy supply equal to 1,000 times the mass of the sun just to produce a single Planck energy neutrino.
And right here lies the ultimate paradox of exploring the micro-universe. Usually, trying to probe smaller distances means you just hit things with higher energies. But at the Planck length, this logic flips completely. Higher energies would just equal bigger black holes. If you collide particles with enough energy to probe below the Planck length, you wouldn't reveal finer details of spacetime. The massive concentration of energy would just instantly create a tiny black hole. You physically cannot measure a distance smaller than this. Nature simply will not allow it.
Which brings us to part 2, the ultimate unification and the ongoing quest for quantum gravity.
Because we physically cannot experiment at this scale, we're pushed to the absolute frontiers of human thought. Leading theoretical contenders to solve this include string theory, loop quantum gravity, and doubly special relativity. These frameworks attempt to bypass the breakdowns of our current physics. They're trying to mathematically unite the smooth curves of gravity with the jittery, probabilistic quantum realm, hoping to finally give us a set of equations that can survive the extreme conditions of the Planck scale.
The overarching goal of all these theories is to crack the quantization of space-time. Max Planck discovered that energy comes in discrete little packets, or quanta, which essentially launched the quantum revolution. Today's physicists want to figure out if space and time themselves are also quantized. Are they continuous, like a perfectly smooth sheet of paper? Or are they built out of discrete, indivisible building blocks? If physics fundamentally breaks down at the Planck scale, and if you cannot physically measure anything smaller without creating a black hole, could it be that the smooth, flowing universe we experience every day is essentially a trick of the light? Could it all just be an illusion built on top of a tiny, pixelated reality? The Planck scale shows us the absolute limits of our current knowledge, but it also points directly to the next great revolution in understanding our cosmos. Thanks so much for joining me on this explainer, and remember, keep questioning everything.